Our first speaker will be Dr. Alex Thomasson. Dr. Thomasson is a professor of biological and agricultural engineering at Texas A&M University, where he has taught and conducted research since 2005. His areas of expertise include precision agriculture and remote and proximal sensing, and he has recently been heavily involved in the use of unmanned aerial vehicles in agricultural research. Dr. Thomasson was previously a faculty member at Mississippi State University, where he served as Agricultural Research Coordinator for the university's Remote Sensing Technologies Center. Prior to that, he served as a research engineer for USDA's Agricultural Research Service. He holds a PhD degree from the University of Kentucky, an MS from Louisiana State University, and a BS from Texas Tech University, all in agricultural engineering. Dr. Thomasson is a registered professional engineer and recently retired from a 22-year career as an engineering officer in the U.S. Navy Reserve. Now I will turn the program over to Dr. Thomasson.
Well, let me first just say thank you to the participants. I appreciate your giving me the time to talk today about our program at Texas A&M. Randy Price, who will be speaking after me, I think is going to give some practical application discussion. My discussion is principally focused on the comprehensive research project that we have at Texas A&M in agricultural remote sensing and high throughput phenotyping with UAVs. And I'll try to work through some of these terms like high throughput phenotyping that some of you may not be familiar with as we go through the presentation. As I said, we have a comprehensive project. I have 4 teams listed here that are part of the project, and I really should probably add an additional one. That would be our administrative team. The administrative team is based in our Texas A&M AgriLife Research Agency, which is basically our state agricultural research experiment station. And they have provided funding for us for the first year and are funding us for a second year now. And basically they pull us together for meetings, keep us on track, assist us in writing proposals and that type of thing. But in terms of the day-to-day function of the project, we have 4 teams. We have 3 groups that make up our flight team. We have a sensors team that I am the lead on, the data analysis team, and the field research team, and I'll describe each of these as we go through. Our flight teams, again, we have 3 groups. One is led by Dr. John Velasic. He is an aerospace engineering professor here. He is also the director of the Center for Autonomous Vehicles and Sensor Systems, CANVAS. And excuse me, they basically fly 3 different aircraft. One they have designed and constructed internally called the Pegasus, and you'll see a video on that in just a moment. They also have a couple of commercial fixed-wing aircraft. The main one that we've flown is the Anaconda, and I'll show you a picture of that as well. Dale Cope is a professor in mechanical engineering. He has an arrangement with the company Precision Hawk to have access to one of their fixed-wing aircraft and camera systems, as well as their cloud-based support services. And also Dr. Soren Popescu, his group flies rotary wing aircraft. He is a professor in the Ecosystem Science and Management Department. Dr. Velasic is towards your right, the tall fellow in the sunglasses. The Anaconda there is shown. This was really our principal aircraft for the first year, flying a number of different sensors, mainly multispectral cameras. And on the far right there is Dr. Yayin Shi, who works with me on the sensors team, and I'll talk a little bit more about what she does in a moment. So I'd like to go ahead and cue the first video. That is the Pegasus aircraft. It's the one that was internally designed, developed, constructed by Dr. Velasic's group in aerospace engineering. Most of the work that we've been doing on this project has been at our research farm that is a few miles away from campus. What you're seeing in this video is not our research farm, but what we call Riverside Campus. So the Riverside campus is actually an old Air Force base that belongs to the university now, and it's mainly belongs to the College of Engineering and the Texas Engineering Experiment Station. The video is showing you we have a couple of GoPro systems on this aircraft, and we have a multispectral camera that's looking downward, and we're able to snap multispectral shots, and you're seeing color infrared images of some of the vegetation and the airstrips on that location. This aircraft actually has the capability of about a 30-pound payload. That's one of the reasons we haven't been using it as much, because most of our payloads are much smaller than that. And this is the other GoPro camera that is actually underneath filming it, so you can see what's going on at landing and takeoff, which really becomes more important when we're out at the farm, because we don't have paved runways to take off and land from there as we do at Riverside. So as this video ends, I'll move from talking about the flight teams into the sensors team. Again, I'm the lead on the sensors team. I have a number of graduate and undergraduate student workers on this, and Yayan Shi, who I showed you in the picture earlier, is basically my right-hand person on this, but she works broadly across the entire program. She's an assistant research scientist here, and our role is to help write the specifications when we're procuring sensors, to make sure that the sensors are appropriately configured and installed on the aircraft, to download the data from them, and then to help all of the scientists develop data analysis and image analysis techniques for their use of the images that we're collecting. Third, we have, as I mentioned, the data analysis team. The leader on this is Dr. Michael Bishop. He is a professor in the geosciences department, and also he is director of GeoSat, which is the Center for Geospatial Sciences, Applications, and Technology. His principal person working on this project under him is Jeff Olsenhaller. And as I go through this, I'll sort of explain the workflow a little bit to you, but when we collect images on an aircraft, we immediately take the data card from the aircraft once it lands, and we take that to Jeff, and Jeff begins the work of mosaicing, so we can quickly provide good data to the researchers involved in the project. Then we have the field research team, and this is really the key component. This is where most of our scientists are, and I would say that we have almost 40 scientists across the breadth of the project, and the majority of those are on the field research team. This involves several breeders and geneticists who are doing high throughput phenotyping. I use the acronym HTP here for that, and you'll note that that name was in the title of the presentation. So I'll go ahead and explain high throughput phenotyping here for those that may not be familiar with it. Breeders have historically collected data on growth parameters of the plants that they're interested in breeding, and we'll just take a cotton plant for example. They might collect information on the number of bolls at a certain time, on how tall the plants are, on how drought tolerant they are. All of those measurements are called phenotypic measurements, and they're typically made by technicians and students, graduate students, walking through the field with measuring devices, which may be a yardstick or what have you. And the fact that those measurements are made manually limits the number that can be made, and so it limits the number of varieties or strains, if you will, of a plant, or lines of a plant that a breeder can work with. Now that we're dealing with high throughput phenotyping, which involves autonomous sensing systems like UAVs with cameras and potentially ground-based robots and so forth, we can collect phenotypic measurements on a much larger number of plant lines. And because we can measure genetic properties of plants so easily, then the breeders and geneticists are able to make much more rapid progress in the improvement of crops, because they have all of this high throughput phenotyping data now to work with. So that is a significant chunk of our field research team. The other chunk of our research team is probably the larger group, and that's really agronomic research. I use the acronym PA here for precision agriculture. because they're largely looking at variability in plant health and plant traits and soil traits and so forth across the field. So this is everything from soil scientists to agronomists of various sorts to weed scientists and so on. The equipment that we have, as I've mentioned and shown, we have multiple fixed-wing aircraft. The Anaconda has been our principal aircraft. The Precision Hawk Lancaster is available to us, and I've also shown you the Pegasus. We also have a rotary wing aircraft, the Turbo Ace X88, that is operated by Dr. Popescu's group. This just gives you a picture of these three systems. And I'd like to go ahead and queue up the next video now, and I'm going to show you a little bit of our operations with the rotary wing aircraft that Dr. Popescu's group uses. If you're not very familiar with the use of multiple types of UAVs, I would point out that probably the biggest difference in the way that you use fixed wing and rotary wing UAVs, we may be having a little bit of a bandwidth issue. I think this is a little choppy, at least on my end. But hopefully you'll get the sense of what's going on here. The rotary wing aircraft fly relatively slowly, but they can hover, which is great. So if you're looking for very highly detailed images of crops and so forth, rotary wing aircraft are ideal because you can have them fly low and slow or even hover over a certain location, which gives you much higher resolution in the images that you're collecting. Now, on the other hand, if you are trying to cover a lot of ground, a large field or a large farm, you're not going to be able to do that very easily with a rotary wing aircraft, and so then you really need to graduate to fixed wing aircraft, and you begin to have to deal with issues like how fast the aircraft is traveling relative to the exposure time of the camera. And I'll talk about that a little bit more as we get on further into the presentation. A couple of things I would point out. You're seeing that we have multiple plots and fields out at the farm, and because we're getting highly detailed data with this type of UAV, and we've got a lot of overlap in these images, we're able to not just calculate mosaics, but we're able to calculate some three-dimensional structural properties of the plots and plants, which enables us to measure things like plant height. And I tell you what, I think we'll go ahead and stop this video at this point. I think I've made most of the points I want to make, and we'll move on to the next slide. So I've mentioned the aircraft that we have in terms of equipment. We also have quite a few different sensor capabilities to work with. We have multiple multispectral cameras, and when I say multispectral, I just mean that each one is collecting image data from various portions of the spectrum, and that can be anything as simple as an RGB or basically visible color camera up to including cameras that have multiple bands, but something below hyperspectral, which means many spectral bands. So we've got multiple multispectral cameras. We've also got a state-of-the-art hyperspectral camera that has about 400 to 1,000 nanometer capability and collects 900 bands, so very large number of spectral characteristics are in each of these images. We also have a LiDAR system, and we're in the process of procuring probably about as high quality a thermal camera as it is possible to purchase from FLIR. Now the one I'm going to show you in just a moment some pictures of some of these, and the thermal camera that I'll show you is not the actual one we're purchasing. It's just sort of a stand-in picture. But in terms of the multispectral cameras, we have two different Tetracam models that we've been using. The Tetracam ADC is the one that we have flown the most on the fixed-wing aircraft, the Anaconda. But over time, over the course of the last season, we gravitated to the Syntec GEMS sensor, which we found to be quite good. Also, the Nikon 1J3 is a solid camera that we have used a good bit. In that one, we've got configured to give us green, red, and near-infrared bands. And then we bought a Nikon DSLR camera that is just RGB, so it's visible color, but it has very high resolution. So we've been able to get some highly detailed images, even from our fixed-wing aircraft, down to the pixel level of a few millimeters, which ultimately, particularly for the high throughput phenotyping purpose, is what we're wanting. So on the left in this slide, you can see the Tetracam ADC Micro. In the middle, the Syntec GEMS sensor that I mentioned is probably the one that we've mostly begun to work with. I would point out about that one that it has two cameras in it, and one of those cameras is used to collect RGB, or red, green, blue images, and the one that is mounted right next to it, so it's basically collecting the same image at the same time, collects only a near-infrared image, and those 4 bands are overlaid in the software after the flight. And then on the right, you just have the standard Nikon DSLR camera. And you'll note the differences in these are pixel resolution, not a ton of difference between the Tetracam and the Syntec GEMS, but quite a bit higher resolution with the Nikon camera on the right. As I mentioned, we also have a hyperspectral system that is built by Headwall Photonics. V-near means visible and near infrared. And again, I said it's about 400 to 1,000 nanometers and 900 bands. We also have the Velodyne HDL32E LiDAR system, and we're in the process of purchasing the FLIR. It's actually an AD6751 SLC, and we are putting in paperwork to make the purchase on that even today. The thermal camera that you see in the middle here, again, I said it's just a stand-in. That looks nothing like the model that we're actually purchasing, but the thermal image shown there just gives you something of an idea of what we might see with the camera that we're purchasing. The LiDAR instrument on the left is being flown mostly from the Rotary wing aircraft, and then the hyperspectral system on the right. This is actually the type of system that we have for hyperspectral analysis. With each of these camera systems, we are flying with GPS, Global Positioning System sensors, and IMU, which stands for Inertial Measurement Unit. With both of these, we're able to, for every image, know where the aircraft was when the image was taken and the attitude of the aircraft. So we can tell, the vantage point and the viewing angle of the camera, which helps us as we're processing our images into mosaics to know exactly what the camera was looking at when it took that image. So we also have a good bit of computing hardware and software that is mostly housed in GeoSat, the center that I mentioned previously. The software that we've been using, Pix4D has really been our workhorse up to this point. It's a really high quality mosaicing program. That's not all it does, but it's very good at that, and we've been using that. Envy is what we are mostly using for image analysis, but also MATLAB, and of course you see ArcGIS and ERDOS there as well. So our goals in this project, and again, this is a large comprehensive research project, our goals have been to provide, I put in quotes here, next day, because really 48 hours is probably more accurate to what we're able to do. But next day data to the field research team, and what those data include are mosaic route pack images. I'll explain to you in just a moment what a route pack is. We want those data to be high resolution as much as possible. We want them to be geographically registered, which means that when you look at one pixel on the image, you know exactly where that pixel is in the field. And we want them to be radiometrically corrected, ideally, which means that if you look at a particular plant and the image is telling you that it is reflecting a certain amount of light and a certain wavelength, that's actually the correct amount of light it's reflecting in that wavelength. So some of our requirements to meet the goals have been field preparation and logistics and data processing and data analysis. So I'll go into these just a little bit. Field preparation has meant runway preparation. If you're dealing with fixed wing, not all of them, but most of them need a place to take off and land. We also need ground control points so we can do geometric correction on our images. We also need calibration targets for radiometric correction. We have actually combined our ground control points and calibration targets into one system. And as much data as possible so that we can relate our images to things that are going on in the field. And by that I mean like variability of soils and so forth. So this image shows you our ground control points that are also doubling as reflectance targets. We're using currently 2, but we're graduating to 3 in the coming season. 3 painted tiles with known reflectance values on them. The black paint that we use is about 4% reflectance. The lighter gray paint about 40%. And so whenever we fly, we go out and we actually measure the reflectance of these tiles because we know that the paint will change somewhat over time, and we want to do a really good job of doing radiometric correction. We put these out in the field permanently so that we don't have to go out on a regular basis and lay out something like a calibration tarp. We ultimately take the images that we've collected and we put them into Pix4D and build a mosaic. As you see here, the image on the left is of one of our fields. This is an RGB image, or normal color image, that was made up of something over 1,000 individual UAV images and mosaicked into one geometrically corrected image. On the right is an NDVI of that particular image. NDVI stands for Normalized Difference Vegetation Index, and the lighter colored areas in the field tend to indicate where the healthier vegetation is. The darker areas either where the vegetation was less healthy or there was less of the vegetation there. In terms of our logistics, we had to make flight plans. We have a 1,400-acre farm that we're working in. It's made up of a number of research fields and plots. We broke those up into route packs, and we have flown most days. One team or another has flown on most days during the season. This slide I just threw up there, this shows you the number of flights that we took starting on June 6th through September 12th. We continued to fly into the fall beyond that, but we were flying quite regularly and collected, for lack of a better term, tons and tons of image data. Now this is our farm that's just a few miles from campus that we're working in almost on a daily basis. Again, it's about 1,400 acres of crops, and you can see that we've broken the fields and plots into these sort of contiguous areas that we call route packs, and that enables us to make nice, efficient flight scheduling. We know whose fields are in which route packs, and we can communicate between the flight teams and the field researchers in terms of what needs to be flown when. Logistics have also involved monthly team meetings. Again, we've got at least 40 people there every meeting. Coordinate with farm regarding the aerial spraying. What that means is that we've got a farm manager, and whenever they're spraying, he needs to let us know. Whenever we're flying, we need to let him know so that we don't have any problems. I jokingly refer to our data distribution method once we take the data card from the aircraft and take it to Geosat so that they can do initial processing as SneakerNet. That just means that we're hand walking it over there with our sneakers on. This is a typical day. We take our Anaconda fixed-wing UAV out there. We fly it at about 375 feet. We typically do this with this aircraft twice a week. Fly ground speed is roughly averaging 35 miles per hour. Time of flight averaging about 25 minutes, and we're commonly flying the Syntex sensor. Because we need a lot of overlap, we have done a lot of testing of different flight patterns. These are input into the computer beforehand, and then the aircraft flies these flight patterns based on the controlling computer and the GPS data it's collecting. This image just shows you with the DSLR camera some of the higher resolution data that we got. In the upper right, you see an image that shows you some pretty high-level resolution on some corn plants in the field during the season. A couple of final slides here as I begin to finish up. One thing that you have to do is you have to look at what your resolution is going to be for a given altitude. With the systems that we're using, we're typically flying about 400 feet, and you can see that on the left graph that our pixel level is something below 2 inches or below 50 millimeters. Also, our velocity needs to be in the 40 range, and I think I've already mentioned that we're typically flying about 35 miles per hour. A couple of lessons learned before we wrap up here. Resolution depends on flight and camera, but it also depends on the speed of the aircraft. You can fool yourself into thinking that you've got really high resolution, but if your aircraft is moving faster than the exposure time of your camera, then your pixels will be smeared and your resolution isn't what you think it is. So that's really a big issue. The onboard GPS and IMU accuracies need to be high if you want to do a good job of using those data for mosaicing. You also need a good bit of overlap in your images, and you need good ground control points. Ideally, you have a stable airframe that keeps the camera pointing down most of the time. That requires precise aircraft controls. And if you can afford to, it's also nice to have a gimbaled camera, which tends to keep the camera pointed down regardless of the attitude of the aircraft. Radiometric calibration is important, particularly from a research standpoint. We chose to use permanent targets. We make regular reflectance measurements on those targets to make sure we have up-to-date data on them. Clouds can be an issue when you're flying. It maybe takes you 20 minutes to fly over a big field, and during that 20 minutes you may have small clouds fly by that give you some problems with understanding what's going on in your images. Now, this is my last slide. I just want to ask a couple of questions. What is it that you want? If you're a researcher, you may be wanting high throughput phenotyping data, and then you're going to err on the side of getting very high resolution data. If you're more of an agronomy or farming type person, you're looking at precision agriculture data, variability in the field, and then you're probably less concerned about the resolution of the images. It's important to know that there is a lot of overlap between these two fields, but sometimes you have to decide one way versus the other in terms of what you're interested in. The last comment I would make is the use of UAVs in agriculture another all hype situation, like a lot of people think that precision agriculture was maybe 20 years ago. I have been in precision ag for that long, and I think the answer to that is no. I think that UAVs are going to be heavily used in a number of fields, regardless of what happens in agriculture, that the technology is going to continue to advance. And because of that, I think that we're going to continue to see advances in agriculture. And my thought is that 5 years from now, people are really going to know how to use, at least in minimal level ways, how to use UAVs to help them in their agricultural production systems. And with that, I will sign off and thank you all very much for your attention.
Thank you, Dr. Thomasson, for an excellent presentation. And I want you to notice that in the chat box to the left, you've got a question from a participant. So if you could, if it's possible for you to type the answer, otherwise we'll try to answer it on the microphone at the very end. But again, I want to encourage participants to use the chat box to ask the speakers specific questions. So we're going to move on. Our next speaker will be Dr. Randy Price. Dr. Price is an adjunct assistant professor and agricultural engineer with the Louisiana State University Ag Center. He has numerous peer-reviewed publications and patents that have resulted from his research career. Dr. Price is currently focused on application technology and precision application issues and will be discussing the nuts and bolts of unmanned aircraft systems, including sensors, building, and testing. So I'm going to turn the microphone over to Dr. Price.
Thanks, Jim, and good afternoon to everybody who's out there. Like Jim said, my name's Randy Price, and I work for the LSU Ag Center. And instead of being located at a main university level, I'm actually located out in a field office. And so a lot of my presentation will be why I'm here, and that's to really help the farmers and producers understand these devices and what they can do with them. And that's kind of what we concentrated on. We do a little bit of research, but a lot of that research is spurred on by questions that the farmers ask. And Louisiana contains a lot of different crops, so sometimes our questions are quite different, you know, than maybe the people in the Midwest address. For instance, like we have rice fields, and it's always a question, well, what if I, you know, land my UAV in the rice field? Well, you know, we've got to look at ones that are waterproof and different attributes and things. So we do have a lot of different needs here that can tend to vary from some of the other states. I'll talk a little bit about the unmanned aircraft in agriculture and some of the stuff we found out about these units. First of all, we always get a question a lot of the farmers ask, you know, what's the possible uses in farming? And at least in Louisiana and probably across the country, there's a lot of uses for these devices. One of the main uses that we've heard about is the overhead imagery of crops and fields. This has been going on probably since the 60s and 70s and 50s. You know, there's been remote sensing. People have wanted to use it to tell things about their crops and do a better job applying either nutrients or fertilizer, or you know, somehow get a value increase on their farming areas. Well, in the past, that's been extremely hard. You know, we had satellites and things. They worked good, but there was cloud covers. The visit times weren't quite high enough, things like that. You had to deal with a party in between you and the actual photos to where you had to pay to get it, and lots of other things. So, there's also manned aircraft. Those have been used in the past. We've used them in the past. Also work pretty well, but you still got a little bit of expense trying to get the airplane to where you're at. Sometimes that person's flying, an hour or two away, which isn't very far in an airplane, but by the time he gets to the field you want to take a picture of, it's cloudy or something's not quite right, and he goes home, and then we just never get the photos. So we're kind of hoping that these UAVs, and what we're seeing is they're going to probably give you as an individual a real tool to get out there and get high quality, really quick photos and imagery of fields in a fast manner that you kind of control. Like if you go out there and it looks like a nice day, you can just go out and get that data. We've had a lot of talk here in Louisiana. There's a lot of crop scouting and crop consultants, and these devices will have a high possibility of helping them be able to get up over a crop. Instead of an oblique view where you can't really see much, we can get up kind of high and really hopefully define the areas where you may want to do some checking for insect damage and things like that. We always get this type requests, and that's even taking images of machinery and farmsteads. Every time we've been out flying a field, sometimes there's harvesting operations or something like that going, and the farmer's just curious, hey, I'd like to see what it looks like from the air with my machinery harvesting, and it's always kind of interesting to see. And while he's looking at that, a lot of times he'll see his field and he'll notice variances and say, oh, that's weird, those 3 or 4 strips or rows are completely different than the other. And then it causes him to think back and think, well, what happened there? Is that a different variety? Did the fertilizer truck run out of fertilizer? Things like this. So it seems to help out. I know in the Midwest we don't have as much center pivot irrigation here, but trying to check nozzles and things in irrigation systems is a very lucrative use for these. Here in Louisiana we do have a lot of flood irrigation, and these have been theorized, even tested last year to try and get to the back of fields. At first you think, well, that's not a hard problem, but some of these fields are about 300 feet long. You're trying to flood irrigate them, and the farmer wants to know when the irrigation water hits the back of the field so he can turn the pump off. Well, a lot of these fields you can't drive back behind them, and now with poly pipe and quarter drains and stuff, it makes it even harder to get back there. So there's a lot of theory. Even some of the visual feedback from these devices will be used for that. Of course, spraying is a big one. Here in Louisiana, there's a ton of spraying that goes on because of rice fields and things like that. A lot of these fields are being encroached by suburban areas, and they're still in production for rice. We want to, keep our good land in production if we can to make food. And but the airplane pilots are having a hard time getting into these areas, with something as big as an airplane. So it's theorized, and even some of the airplane pilots are interested in this, that this might be a side business for them to run. A UAV is an aeronautical aircraft. It's going to be governed a little bit by the FAA, that they may have a small business where they take these units out, and even though they can't cover a lot of acres, they may be able to cover the hot spots, where they don't want any drift near, vegetables, crops, tomatoes, maybe a person's house, things like this. So even though that doesn't sound that practical because of the weight that's required to, lift spraying systems, it does make some sense on the small side. So there's always checking farm areas. We've already had cattle people using these. They don't want to drive to the back of the field because it may be muddy. They got open gates, things like that. They're starting to use these where they'll fly to the back of the field and actually count their cows and then fly back. They need to drive in, then they'll drive in. If not, they'll go to the